Gordon's thing is working, by the way. I can see it.
Yeah, we should be recording now.
Great, great. Welcome, good people. Good evening again. Welcome to our PyData Triangle March event. I'm so glad everybody can join our online event, and I'll go ahead and start introducing our presenter, Gordon Hart. Sorry, Gordon Hart. I'm so sorry. Okay. How do you pronounce your last name, Gordon?
Just Hart, like the organ.
Hart. Great. Thank you. Thank you for correcting me. Gordon has been working with machine learning and big data for years. And according to her, according to some comment from Gordon, after being burned too many times by unexpected mission-critical model performance in production, Gordon co-founded Coiled to build a machine learning testing and evaluation platform to tell you what you need to know before your model hits the real world. Thank you, Gordon. It's all yours. Thank you.
All right, and thank you for that intro, Yanlei. Today I'll be presenting a presentation called Test-Centric ML Model Development. Before we get into it, I really want to extend some thanks to Dhruv and everybody from PyData Triangle for having me on tonight. I'm very happy to be giving this talk, and I'm hoping that if you are training models, this can provide you with a little bit of additional perspective and maybe help you think about your problem in a different way. Or if you're not training models, help you understand some of the difficulties that come from pushing models into production and some of the ways that you might actually successfully achieve some goals that you have in that object. So I'll try to leave some time at the end for questions and discussion, but without any further ado, let's get into this. A little bit of an introduction, who I am, why you should listen to me. I've designed, built, and deployed AI products for DoD and DHS customers, including the Army, Air Force, Marine Corps, and then some DHS people like TSA, Federal Protective Service, and other groups within that organization. I was the first engineer at a startup called Synapse that was acquired by Palantir, building ML products for the security domain. I worked there at Palantir building ML products, and I co-founded Coiled, as Yanlei mentioned, where we're making a machine learning testing and debugging platform that is hopefully going to tell you some things that you'd like to learn before you have real results on the line here. So with a little bit of a disclaimer, these are slides adapted from some pitch, but I'll try to keep it general interest and focused on the problem and some sort of the general things about what a solution might look like, and just spend a little bit of time at the end talking about our particular solution. And in this focus on designing and operationalizing AI products here, it's a bit of a different perspective from one that you might have as a researcher. I'm focusing particularly on actually getting results and making sure that we're using this technology effectively to achieve whatever objectives you have there, and not just iterate better and get higher and higher metrics on some benchmarks. And in that process, I think the main thing that I've learned is that you really can't trust ML to work as expected. And to illustrate this, let's look at a case study where this is motivated from some experience at Synapse, where our ML team spent months improving the statistical evaluation metrics for a product that was trying to detect guns in security X-ray scans, things like what you see on the right here. This team was getting better and better with their models. The amount of data that was going into them was increasing quite rapidly. The model architecture was getting more and more cutting edge and state of the art. And our ability to accurately train our models and tune our hyperparameters was increasing as the team was maturing, and our understanding of our domain was as well. And we get to this point where we have a model with a 99% F1 score, with 99.5% recall or greater than that, and less than 99% precision. And so what this means, if you're not familiar with these metrics, is that with a 99.5% recall, you would expect only 1 in every 200 scans of a gun to be missed by this model, to not be detected here. And then we presented these statistics to a customer, deployed this model out into the field, And the model missed a very obvious case, something that looks almost exactly like what you see on the right, where a gun was just placed in the center of a bin. This is like an X-ray scanner that you'll find at an airport or something like that. And so imagine those plastic bins. Gun was just placed in the center of the bin, run through the machines. It goes through our system, and sure enough, misdetection. This is a single occurrence that has pretty extreme consequences for a mission-critical ML product. You lose trust with your customer, and lost trust is irreparable to some extent. There is very, very difficult time reestablishing trust that you've lost by poor performance, and particularly by poor performance that blindsided you. On our end, this kicked off a long time spent investigating why this happened, collecting additional data to make sure that we're training models for which this wouldn't happen, and then retraining those models and validating that this doesn't happen again. And then in our processes, we collected all this additional data and we made sure that it was being used in training, and those samples were included in testing. But that whole process provides us with no guarantee that this bug won't reappear. And as we're training models daily and pushing new models out weekly, things like this, silent regressions in behavior, are something that you really need to be careful about. And what this really comes down to is that the current ML evaluation approach that we have is falling short. You'll spend a lot of time collecting and annotating data, and you will arbitrarily split that into some training set, validation set, and then test set that you finally use to produce these metrics. And so you train models, and they get better and better here. They trend closer and closer towards zero loss. And especially if you have things that are getting up around the 99% error area, you are succeeding in a lot of cases and failing in relatively few cases here. And you keep iterating on your models, you try different architectures, you try different hyperparameters, and you watch these loss plots get better and better. And then you produce a global metric like 99% F1 score that is produced by performing inference on all of this benchmark data set, your test split there. You perform inference on that and produce some global metric that says, you know, we're 99% good at detection in this case. And that metric fails to tell you really anything meaningful about the model's behavior here. And typically, since when you're iterating from one model to the next, you want to make sure that you have, you're comparing apples to apples here. You'll typically freeze this benchmark data set. You'll set it at the beginning of the year, and then you'll do the next 6 months of model development with the same frozen benchmark. And your main objective is optimizing that global metric on that frozen benchmark here. And that really fails to tell you anything about what you can expect from your model in the field. And one of the main reasons for that is something that's been labeled by research as the hidden stratification problem in the past couple of years. And to understand what the hidden stratification problem is, let's look at the specific case that motivated this paper here, where a researcher was trying to reproduce some results from another paper, trying to classify the presence or absence of cancer in chest X-rays. And he was able to use the same model as the other paper and reproduce the same results here, and get the exact same numbers. And it seemed like that was a successful reproduction of that paper. But when he looked into it as a researcher, he found that there were statistically meaningful subclasses within the main class of chest X-ray with or without scan. And so when you're training this classifier, you'd feed in this chest X-ray, and you are training against the ground truth, has cancer or doesn't have cancer. And you're training a classifier model to try to discriminate between images that do and do not have cancer. But that single label, has cancer, has a lot of subclasses within it, hidden strata that are meaningful when it comes to the predictive ability of the model to accurately classify them. And in this particular case, this researcher found that a majority of the successfully predicted examples here, these chest X-rays, were examples that had something called a chest drain, which is a palliative procedure that's used to reduce some of the symptoms of late-stage chest cancer. And the model was actually learning to use the presence of a chest drain as a predictive indicator. And when he removed these scans with chest drains, you'll see here on this receiver operating characteristic plot over here, that's plotting true positive rate versus false positive rate as you vary threshold, as you vary confidence threshold. And so something that looks more like an L, like an upside down L, is a better performer, has a better ability to accurately classify examples. The meaningless case, the ones with chest strains where the model was just looking at the presence of a chest strain, was very, very good. It had generally quite good performance. The area under the ROC curve being 0.94, meaning it's getting close to a perfect classifier there. The aggregate metric here was a little bit less, but still quite good, 0.87 AUC. And the actually meaningful case, the one that you care about in a clinical setting, the classification of has or has not cancer for images that do not have chest strains, was severely underperforming here. You have your AUC of 0.77, which means that this has very little utility as a classifier and is very far away from something that you would expect to use in a clinical setting here. And this is a particularly poignant example of the hidden stratification problem, but this exists all over pretty much any domain that you'll be trying to develop a model for. Global metrics fail to capture the full picture here. This AUC that you have on all of these, on all of the examples aggregated, doesn't actually tell you what your performance in the cases you care about is. And typically models will exhibit highly variable performance across these different subclasses. And since you're just looking at some global metric here, you can improve greatly in one subclass that you don't care about, like the one with chest strains, and regress in one that you do care about, like no chest strains, and have that masked, have that failure be masked, this regression be silent, because you're looking at only the average of those subclasses. And this is a problem that exists across the industry. And for the same reasons, a lot of important questions when it comes to deploying models and trying to successfully build ML products are extremely difficult to answer. If you've been involved in this effort as an engineer, a scientist, a PM, an engineering lead, a business person, even a customer trying to buy them, you have likely been on one end or maybe both ends of these questions and seen how difficult they can be to answer. Basic things like, what are the model's failure modes? When can I expect it to succeed? If I'm pushing a new model, what has improved or what has regressed? If my model has improved by some arbitrary delta in global metric, how is this improvement distributed? Can I expect better performance in all scenarios, or is it localized to a particular scenario? If I have a certain deployment with certain conditions and I have multiple models, maybe a couple of new models that I've been training and some past models that I've released, which model is going to be best for those circumstances? Which model should we deploy? And then the big question, which is very, very difficult to answer typically, how do I know if my model is ready to be deployed? And this is the scary one that you really like to have a good answer for, but often you don't. The way that we solve this problem is with a paradigm shift to something that we call test case-based evaluation here. It involves a fundamentally different way of thinking about your problem. It takes from a world where we have a test set represented like what we have on the left, which might be unbalanced across subclasses, might be arbitrarily split. With our train val test split, we'll take some random sampling of this big bucket that we're using to both train and evaluate our models. And we'll freeze this benchmark data set and have these different colors might represent different subclasses. We'll just have those randomly scattered around in this test set. And test case-based evaluation involves migrating to a world where you actually sort those colors into different test cases. And you take your one benchmark and break that benchmark data set into many different, more tightly scoped test cases that are attempting to assess behavior in a very specific scenario here. And when we're looking at the case of the X-ray gun detector, some of the fine-grained test cases that we would care about are things like gun in an empty bin, a top view, maybe a front view looking at the sensor, or a back view looking away from the sensor. Guns in low occlusion environments, guns in high occlusion environments, high blur if you have an old or an uncalibrated X-ray sensor. And these would be the sort of test cases that you would be looking to create in order to understand your model's behavior. And when you create these test cases and evaluate your models on them, you get high resolution test results here. And to illustrate that, we'll look at this example where we have two models labeled Model A and Model B on the left and the right. We've produced a global metric on our benchmark data set where Model A is 97.8. Let's say this is F1 score, the harmonic mean of precision and recall, but it could be anything, whatever metric you use as your North Star as a team. And Model B has 99.2 on this global metric. When we look at this at the test case level here, we see that model A has quite good performance across gun and empty bin, back view, front view, low occlusion, and very, very poor performance in high occlusion and high blur circumstances. Model B, on the other hand, has middling performance in gun and empty bin, and then good performance across back view, front view, low occlusion, and also pretty good performance in high occlusion and high blur. But all of these different scenarios don't matter to your product equally. You should assign some product criteria to them where we can say things like a gun and empty bin is a critical behavior that our product needs to have. And when you use that, you can say, based off of my product criteria of this being a critical example, these others being important, and then these bottom two, high occlusion and high blur, being irrelevant, you can make the call that model A, which has the lower global metric, is actually better aligned with the objectives that you're trying to achieve here. And then you can choose to deploy that model and likely achieve better results in the field. So the process here is something that we call test-centric ML model development here, where in the middle of all of the moving parties that are involved in training and deploying ML models, the central item is your tests. This means that for your ML engineering team, the tests are what's used to guide development and make sure that any improvements in the models are accurately reflected. For the product management team, the tests are what you're using to actually encode your product objectives. If you care about behavior in a certain scenario, you reflect that with a test case of that certain scenario, and then you're able to accurately assess whether or not you are aligning with your objectives or not. And for BD and sales and external parties, tests are how you communicate the behaviors and the capabilities of your models here. And that's extremely important because everything that you know about your model behavior before you push things to production, you learn from your tests. This means that if there is anything that you can expect to see, if there's any behavior or any particular shortcoming that you might have in your model, the only way that you'll surface that before you push things into production and maybe get burned is by good tests that will uncover that. And what this means also is that your testing data is more important than your training data. And this might seem backwards to a lot of people that have been thinking about ML or training ML models, because you obviously need more training data, or that's what the current thinking is. You need more training data, and then your testing data should just be some small set that validates learned behaviors from that training example. That's backwards. The training data is ultimately an implementation detail. The training data, if you have a model that can acquire a certain set of behaviors with 100,000 examples, and a different model that acquires that same set of behaviors with 1 million examples, one of those isn't better than the other necessarily because it used more or less data. What matters is your ability to gain these behaviors, and developing a product, gaining the behaviors involves validating that the models that you've produced actually have them here. And so your testing data sets the target. It says, here's what I want, and it gives you something meaningful to iterate towards and something meaningful to go and collect more training data if that's what you need to do. In our testing data here, there are a lot of pitfalls that you can fall into here. Blind spots can have really unexpected consequences. In this example here that we have illustrated on the right, we have some class, let's say guns and security X-ray scans, distributed across different subclasses A through F. And these subclasses might be things like different occlusion levels or different types of guns or something like that, what have you. And we have our test data distributed between those different subclasses, and the pink representing our model's performance across these different subclasses. And based on the model's performance, roughly being good in areas that are represented highly in our data set, then this model actually looks like a good model, despite having extremely deficient performance in subclass D. And the only reason this looks like a good model is because we have a blind spot in our data set. We don't have subclass D, and that means that we can have very poor performance in that particular scenario and not have it surface to us during the testing process, and that's extremely dangerous. Even if you are to put together a testing data set that is evenly distributed, you can still be misled by the metrics that are produced from it. And here we have an example of two models running on the same test data, where we have roughly even representation across each of these different subclasses A through F. And so our data set has probably been very carefully put together. It's been manually curated to make sure that we're representing each of these different subclasses well. The model on the left has relatively consistent performance across each of the different subclasses. And the model on the right has extreme spikes and extreme troughs in its behavior. It excels at subclasses E and F and is quite deficient at subclasses A, B, and C. And both of these models can produce the same global metric despite having wildly different behaviors. And this is why looking at something that says my F1 score on class X will never tell you what you really need to know, can I deploy this model in a deployment environment that's going to see lots of subclasses A, B, and C? You just can't answer this question, even if you have a very, very carefully put together test data set that has an even distribution. It's important to say here, sometimes it feels a little bit too clear to say, but it's important to always reiterate that your metrics are entirely dependent on the test data that produces them. These performance metrics that you're producing are a function of both the model and of the test data. And that means that when the model is changing and when you're reporting a metric with a new model, the only way that you can actually understand what those metrics mean is if you understand the data that backs it. And very, very few people have a full understanding of the data set that's used to train these models. I would say that it's probably built in the head of the ML engineer who's been leading that particular training push, if he or she actually even has a full understanding of what's in that test data set and how it's distributed. Other people, like engineering managers or product managers or business people or let alone customers, they don't have any of that same context. And so to them, a metric is just a number because they're missing the context of what that test data is. And if you have one model that produces a certain metric and another model that produces another metric, you can report the improvement in that metric, to other people, to other stakeholders, and they can see it as a token that you're doing your job, that you're producing better models. But it doesn't tell them meaningful things about, what is this new model that you're providing me? Is it better at the things that I care about? Is it going to cover some of the failures that we've seen in the past? That metric fails to communicate that. And another thing here is that quality-focused teams spend a lot of time right now ensuring that their benchmarks are evenly distributed because that allows them to think about them more easily. You don't have to think about what some of the hidden biases in your test data set are if it's relatively evenly distributed across subclasses you care about. And it makes the metrics more interpretable to external parties because they don't need to, same thing, build up that state in their head of the distribution of subclasses. And an example here would be if you have a face recognition system, you want that to be roughly evenly split across some of the important demographics that you care about, like age, race, and gender. You want to have an even representation of each of the buckets that you've identified there. And even if you spend all this time making sure that your benchmarks are evenly distributed, you still have examples like this where you don't know what the distribution of your failure cases is within a given class. You can have all your subclasses represented, but you can still be misled by the metrics that are produced on that even data set. So there is a better way here, and those are well-scoped unit test cases. Unit testing is an approach that should be very familiar to anybody who has written software in the past. You effectively want to write a very well-scoped test that is attempting to assert that a desired behavior is present at the smallest behavior, at the smallest level, at the unit level here. And what this means for a ML model is each of these different subclasses, each of these different scenarios could be thought of as a unit. A gun in an empty bin on its side, that would be a unit that we'd want to test. A revolver in a very high occlusion scenario, that would be another unit. And as you're developing this product, you'd want to represent each of these scenarios that you care about in your test data prior to starting any training push here. You would want to get your tests up front and make sure that you have a good representation of each of the different subclasses that you care about here. Speccing out the entire product's desired behavior prior to training is going to yield much better results. The ML team is going to know exactly what they should be trying to build. They're going to know exactly what data they need to go collect and annotate. Product management knows exactly what to expect and has the ability to say, you know, we care about these scenarios and we don't care about these scenarios, and effectively guide the thinking of the engineers that are going to be doing this training. And then lastly, metrics themselves don't communicate much. In general, a metric of 95, 96% versus one of 98, 99, that doesn't really tell you anything. It's not a meaningful piece of information. Oh, I went from 96 to 97. And it encourage teams to think about reporting performance qualitatively across each of these different units that they're testing here. And up top, we have an example of some of the different bins that we'd want to drop performance into. And the range and the particular metric used here, again, F1, and the ranges that you might use for these buckets will change based off of the maturity of your models, how good they are, your particular domain. But in general, you should try to break it down into some human understandable bins like poor, mediocre, good, very good, and excellent. This tells you at a glance here, you have each of these different units for these different test cases. You have their absolute performance, and you can, of course, report the metrics here if anybody wants to see them. You have the absolute performance, and you know I'm mediocres in scenario C, only good in scenario F, and very poor in scenario G, but I've got good behavior on A, B, D, and E. And that gives you at a glance, you know, sort of an expectation of what you can see from that model. And if you report the performance improvement or regression or change in that metric from past iterations of this model, you can communicate the behavior of a model in a way that people that aren't ramped up on the headspace of, you know, these exact metrics or the exact training push or the exact things that went into improving this model, people that don't have that context or people that maybe don't have that technical background can still understand a report like this, which is telling them at a qualitative level, here's my absolute performance and here's how this model got better or regressed across this unit. Talking about test-centric ML model development, I think it's important to ground us in the traditional ML model development cycle here, which we have diagrammed. This is an intentionally constrained view of the world that allows you to focus more closely on model training and treat the actual production of the models as something that's downstream from the business people and putting in their business inputs here. This is the way that you would try to make a model if you were operating in a research lab, maybe without the business inputs. That would probably be a, you know, research goals would go there, and data engineering would maybe be an open source data set or some data set that you get as a part of a grant. And model monitoring, you probably would have model reporting there rather than model monitoring. But this sort of process here, where data is flowing pretty much one way, all of your data is collected up front, there's a lot of iteration on model training and a lot of fine tuning there. This is the old view of the world, which it will train you models that have all sorts of unexpected gaps in their behavior. Training-centric ML is, I think, a byproduct of the types of people that have been training models. Frankly, it's ML engineers or ML scientists or data scientists, and they are bringing a research mindset to it. This is a relatively nascent field. There's been a lot of hype for it in the last 10 years, and it's exploded commercially because companies feel like they need to be having ML teams and, you know, building ML products. And only recently have we gotten to the point where I would say that the model architectures that can successfully achieve objectives are not iterating as quickly as they were 5 years ago. The approaches to successful model training are stabilizing somewhat. There's lots of tools, both open source and proprietary, that you can find for each of the different steps along the model development pipeline. And at this point, it's becoming something that is less of a research discipline and more of an engineering discipline. And productionizing ML is pretty different from lab-based research ML here. And I want to talk here about what we call a test-centric ML model development flow, where the center line, you know, these purple arrows, are all about how we can test our model. Our tests being the central, if I go back to a previous slide here, our tests being the central part of the ML model development process. Everything that we do is mediated through our tests here. And when we have this test-centric ML model development flow, we start from our objectives. And the first thing that we do is we try to define the actual product specifications. This is an important exercise for us to go through because a specification like, I want a gun detector that can detect every gun. That is an unreasonable specification. What different makes of guns? What different scanners are you going to support? What different level of occlusions are you going to support? Do you want it to be able to, do you want to focus primarily on cases that humans are deficient at? You know, if you're trying to make something that's an operator assist system, what levels of assembly are you going to go for? Is it only fully assembled guns? Does that include loaded guns? What about ammunition and magazines? Each of these questions are things that you can plug your ears and sort of la 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 away and push that onto your ML team to try to figure out. But that doesn't help you build successful products here. And so the test-centric ML model development flow shifts that responsibility for defining the success criteria to product managers. And this is pretty critically important because they need to get their hands dirty and they need to look at data and define tests. The tests function as the product specification here. I've said this before, earlier on, and I'll say it again. Your expectations for the behaviors that you want to see in the field need to be represented in tests. That's the only way that you can know that your models are or are not succeeding in those circumstances. And so the tests that you put together, they are the functional encoding of your product specification here. And once you have that encoding of your product specification, you can have this model training flow over here, which involves all of the collection and assembly of training data. Perhaps you're tweaking it, you're going and gathering more, you're getting better annotations. All of that process is actually off of the central path here of the test-based, test-centric ML model development flow here. You can train your models, improve your data, iterate as much as you want, and just keep assessing yourself against this central specification, testing your performance against that central specification, and anything that better aligns with that specification moves on to production here. And that's where you start to see products that are actually succeeding in the things that they were designed to do and having, you know, felt impact in the world. Another big part of this whole flow is that in production, you'll always observe bugs. And observing a bug is something that shouldn't just go and become a new thing. Like, if you shouldn't short circuit the observation of a bug up here and back into assembling training data and then training models and then go back into testing your model and then pushing that out into production. A bug that's observed needs to be reproduced the same way that you wouldn't go and get a bug filed for your software product and then go and write the code change and then open a PR. The first thing that you do is you'd reproduce that bug. You know, does it exist as it was reported? How is it presenting? In what circumstances is it presenting, and in what circumstances is it absent? That sort of reproduction process is exactly what you'd want to do for an ML product. You'd observe the bug, you'd create a test case for it, and you'd put that back into your tests. And you'd use that to better guide the models that you would want to deploy into the field here. One of the things that I want to mention here as well, as when we're on this slide, I want to call out test-driven design a little bit in software engineering. It can be a contentious topic. I think that a lot of people have had good experiences with TDD, and a lot of people have had bad experiences with TDD. And sort of the reasons that it's either good or bad are they don't necessarily apply to the ML domain here. A lot of the difficulty in TDD is coming up with defining interfaces that are easily testable or getting yourself very deep into the muck with mocks. And in ML, the same considerations don't really apply. You just need to be able to make sure that your desired behaviors are represented in tests, because that is the only way that you can actually verify the presence of the behavior. You can't spin up the app locally and click around a little bit and follow the right path and make sure that you have implemented the feature properly. You need to create tests because it's the only way that you can verify your problem. In software, your options are write tests up front, write tests after the fact, or rely on manual testing, and all of those have their position where they're useful, but that's not exact. Those aren't your options for ML. Your options are pretty much set up rigorous tests up front or cross your fingers. And if you cross your fingers, what you'll end up doing is either setting up rigorous tests after the fact and wishing that you'd done it up front, or failing to build a successful product. And that's the unfortunate reality for a lot of teams that have attempted to build ambitious ML products in the last couple of years. This process of finding a bug and creating a test case from it and feeding that back into your tests is something that we might call regression testing for machine learning. Regression testing allows you to fix a bug one time and make sure that that bug doesn't become unsquashed at some point in the future here. As we talked about earlier, you might have a new model that has better performance in certain scenarios and poor performance in some previous scenarios that were bug scenarios. And you might have that regression masked by those improvements in other scenarios here. And you might silently lose that behavior if you don't have a well-scoped regression test in a regression test suite. Regression test suites are effectively necessary in efforts to chase down the long tail during training. Most domains, I would say, are characterized by a lot of common examples, and then common and similar examples, and then a very long tail of examples that get increasingly uncommon and increasingly disparate in presentation, called the long tail. And the long tail problem is what autonomous vehicle companies are coming up against. Most of them have good models that work well in most circumstances, but there's a very long tail of all different sorts of circumstances that they need to make sure they perform well in here. And creating regression tests and making sure that you cover this space is more or less the only way that you can keep your ML team from looking like these kids and playing whack-a-mole, where you smack a bug and then you turn around, you turn back around, and it's back. And that process can be exhausting. It's fun if your age is 4+ and you play it for 15 minutes, but it is exhausting if you're trying to do that and building an actual ML product out of it. Regression tests as well, if we go back to the previous slide, help move us from a world of a more waterfall-based ML development process where we decide what we want to do, we collect a bunch of data, we train, and then we deploy that model, and that is maybe a couple-month process, to a more agile process where as long as we have something that's doing better on our tests, we can push that model. That's something that I think is very important. Agile software development allows teams to operate much more effectively. There's a lot less management overhead once you set up the processes, and it generally gets better features to customers quicker than something waterfall-based. Right now, we're still in the waterfall world in most teams for ML development, but when you have a central model performance test suite that you can use, you can start thinking about ways that you can automate that process here. And automating that process probably involves using some global metric that you want to, when a new model is better on that global metric, you can push that new model out into the field. And I'll say here, global metrics are not all bad. Global metrics like F1 score tend to be bad, they tend to be misleading, but there are certain ways that you can arrange them where they make sense and they actually assess your ability to succeed in the scenarios in which you do need to succeed here. And so if you need a global metric, it should look something like this. An objective function here that's just a sum of each of the different scenarios represented by some performance, and here is where we might have something like F1 plugged in, and some scalar value that we've assigned to that scenario. How important is success in this scenario to us building a successful product here? And when you define an objective function like this, you can say, I care very much about gun and empty bin. Okay, I care quite much about back view, front view, low occlusion, and I don't really care about high occlusion and high blur. This allows you to build automated systems where those model A and model B that we saw earlier in the presentation are actually evaluated against the degree to which they match up with your goals here. And model B was the one that had the 99% global metric and model A had 97%. But when we see that we break it down with these scenarios and we assign product values to these different scenarios, proportional to how much we actually care about them, then it becomes very clear that model A is the better model. And you can use processes like this to set up CD systems where you develop a new model, you run it across all your tests, you generate your objective function value here, and if that's better than your current golden model that's in prod, then you kick that one out and you push this new model out into production here. And if the idea of pushing new models to production without any human decision in the loop scares you, I would say you should think about ways that you can actually quantify what you care about, break it into test cases, and assign values to those. And in the ideal world, you will have the ability to say, I care about these cases this much. And if your objective function doesn't align well with what you actually care about, then your work shouldn't be ripping out the CD system. It should be making sure that you have the right test cases and you have the right values assigned to them. There's odds are somebody within an organization making ML products has something like an informal product value, an informal objective function. They have these weights in their head, and they're going to be making the call, can we or can we not deploy this model here? And this is a very simple scenario here where we just have a linear sum. But if you care about things like bias, you can do things like variance across test cases that are broken down by race, gender, and age. If there's a high variance there, then you can penalize that for your model and say that we only want models that are generally pretty consistent across each of these different important subsets of our data.
Hey, Gordon.
Yes.
Sorry to interrupt. Is it okay if someone asks you several, some questions while you're presenting?
Yeah, absolutely. Sorry, I can't see anybody and nothing.
No, I'll do the reading part. No worries. So there was a question popping up from Matt Phillips.
Okay.
Matt was saying, I'm having a hard time understanding how machine learning is supposed to fix or handle the bugs. For example, I think that's one of your previous slides where you are having the test centralized graphs. Yeah, right here. So Matt was asking, the machine learning tests are model performance tests, aren't they? But the bug fixing is a different set of tests. Is that right?
Yeah, so what I would say here is that, just to be clear, what we mean by a bug is a particular deficiency in model performance in some scenarios. So a model's tendency to fail to detect a handgun alone in a bin, for example, could be a behavioral bug. And this is sort of what we're talking about here, where you would then create a test case with a number of examples of a gun alone in a bin, and you would use that, you'd run your current model on that and verify that yes, you do have poor performance in that scenario, and you would use that test case as the proof that the bug exists currently, and for the next iteration, the proof that that bug is squashed. And for all subsequent iterations, as a part of your regression test suite, as long as you stay green on that particular test case, that regression test with all guns alone in the bin, you would know that you're not regressing on that particular area and that you haven't reintroduced this bug. Does that answer your question?
Yeah, Matt, feel free to unmute yourself if you would like to say some comments.
Yeah, I think I remember from the intro literature that you have your own company. Can I just suggest that you find a different word? Bug means something to anybody who's done software engineering. Bug means something very different and pretty concrete. And as somebody who does both, quite different from a model performance defect, right? I mean, having weights, within a model not where you want them to be is something very, very different from, forgetting a semicolon or anything else that goes by the name of bug, right? And so it's just going to create enormous confusion when engineers and scientists work together if you start calling prediction deficiencies bugs. So just a friendly suggestion for nomenclature. Yeah.
Yeah, that's quite helpful. And we've also heard that using things like test cases can be confusing for people that are coming to things with a software perspective. And it's definitely good for us to maintain a focus on using language that people don't come with all of their preconceived notions about. Any other questions?
I think we have it right now. Feel free to unmute.
Yeah, this is Dhruv. I have it's more of an observation. So if you can go back to the slide where you're maximizing for CIXI.
Yes.
Yeah, this is I don't know, from looking at it from a finance perspective, right? Like this is, or anything else. This is just maximization of expected utility. If you can open that, Wikipedia page, I think it's the exact same formula there. And this is why I find this approach an extremely useful approach, because it kind of ties in the idea of utility back into the world of machine learning performance, which I think is a big miss in the industry right now, which is huge.
Yeah, I really appreciate that comment here, Dhruv. Thanks for saying that. And one of the interesting things that we've seen is teams have also found ways to plug their KPIs into this model objective function and use that directly. Like, how much money are we making per GPU minute that we spend running this model? Things like that, especially companies that can quantify their return on their investment into their ML processes. Companies like that can put together something that is very, very connected to reality as their utility function for their models. And that's quite interesting for us to see.
Great, and a good conversation. Please, again, please feel free to unmute yourself if hopefully, Gordon, you don't mind. This is more interactive session, if you would say.
Yeah, absolutely. Definitely feel free to interrupt me, and I'm going to hopefully blow through the rest of these slides and leave some time for questions at the end, or you can interrupt me in the middle or at the end of any slide. So another thing that you can do to make sure that you're training models that are succeeding is test model robustness by using augmentations here. Augmentations are a very, very common practice for people to use in training, but they're not that common to use in testing. They're ways to make a smaller data set feel larger, and you should be pretty careful about trying to learn too much from your augmentations or relying too heavily on them. They're certainly not a panacea, but they can be quite useful for doing things like assessing your model's robustness to perturbations to the inputs or degradations to the inputs here. And so you can do things like perform an investigation into different lightness levels. You can artificially lower the brightness of a lot of images and see how your model's performance drops off as you get closer and closer to zero for all of these pixel values. If you're making something that uses faces, you can apply targeted cutouts to remove interesting features here, remove perhaps important features like the mouth or the eyes, and see how much your model is relying on those particular features or how much it's able to fall back on additional features when those are absent. And that might do a good job of telling you things like, how well does my model perform when people are wearing opaque sunglasses? If you don't have a lot of examples of that, one of the ways you can easily gather those examples or make mocks of them is with these targeted cutouts. And same thing for the face. It might be a person that's drinking from a cup or something like that, might have their mouth occluded. And this is a good way for you to mock that. And so that's another interesting way that you can improve your ability to test your model's robustness. And another method of testing that you would be pretty interested in as a team that's deploying models is something like integration testing using the exact deployment conditions that you'd be seeing. Often we have models that are trained in something like a PyTorch locally, and they're running on GPUs, they're using 32-bit floating points, and the deployment conditions for those models differ significantly. Maybe you are packaging it for a completely different runtime like ONNX. Maybe you're quantizing it, taking all your weights from 32-bit floating point and flattening them into 8-bit integers such that your model size is smaller and that it runs faster on hardware that isn't float optimized. A lot of these techniques are used for particularly edge devices, including your phone, or if you need to run a model at extreme scale and you can't just afford an unlimited fleet of V100s in AWS. So this is something integration testing with these actual final packaging can surface some pretty important losses in behavior when you're performing these packagings. And there might also be meaningful differences in pre or post processing. For example, in computer vision, most models can't just take an arbitrarily sized input. They have a fixed size input, and you will either crop your image into tiles with maybe some overlap, maybe not, or you would resize your image to fit into the fixed size of the model. This is, if you have a security camera that is producing, like, let's say 640 by 480 low resolution images, and your model was trained on images of all different sorts of resolution, crunching additional metrics and performing integration tests with images that are only the size that you expect to see in deployment is a very important thing for you to tell you what you might expect to see here. And another case would be the shifts in data distribution between your development and your deployment environment here. If we look at the X-ray security case, you have certain things that are relatively low criticality, like water bottles, occurring with an extremely high frequency, and extremely critical things like guns and explosives occurring almost never here. And you might want to run integration tests with images that are more representative of the stream of commerce. And that means that, maybe one image in 10 million is going to have a gun in it. And integration tests like that will give you a much better feel for what it's like to actually use your product. If I'm an operator and I'm using this operator assist product for a week, how many, Chicken Little type false positive detections on guns and explosives am I going to see? If I see one a day, maybe that's acceptable. Maybe I still trust the product. If I see one every hour, my trust and my ability to think that the detections being produced by the system are quality is going to drop off quite dramatically, because I know that this is a relatively infrequent class, but clearly this model is seeing it everywhere. And so those are all important things that you might want to test in integration. Of course, your efforts to understand behavior can't stop at testing. To use another case study here, we're looking at a technique called saliency mapping that attempts to produce a heat map like this. You can render it as a heat map that tells you how much each pixel in the image contributed to the output detection here. And when we performed this on gun and knife imagery, we found that one of the most salient features for a lot of fixed blade knives was this partial tang here, this little piece of the blade that sticks into the handle. And knives that did not have the partial tang, like full tang knives, where the blade extends all the way through the handle, are generally much higher quality knives. We were performing much, much worse on them, despite them showing up much more clearly in X-ray, which renders metal as blue and much more visible. And when we kicked off this investigation, we learned that we were using the partial tang as a predictive feature because we got knives from all different sorts of places. They looked different, but under X-ray, they had one thing in common, which was that they were all very cheap knives that we sourced from overseas, and the manufacturers cut corners there. And the majority of them were partial tang knives that didn't have, more expensive features like full tang here. And the same thing went with handguns. We found that the trigger assembly is something that is a key predictive feature. And when you occlude the trigger assembly or artificially cut it out or remove it from the gun itself, then the model's ability to detect it was significantly diminished. And opening up the black box methods are a good way to supplement the understanding that you get from something like a test case-based evaluation approach here. Rigorous testing is not easy. We've outlined a lot of problems and a lot of ways to solve them, but one of the things that a lot of those solutions share is that it's quite difficult to implement. They're tedious, time-consuming, hard to manage at scale, but the way that you produce models is by putting in the effort to improve your processes, putting in the short-term effort for compounding effects, and we have made Kalena to give you a platform to do exactly that. Help you make more robust ML testing. And I'm just going to blow through these so we can get to the questions here. Part of that is analysis and comparison tools, single model views and multi-model comparison views, threshold tuning to make sure that you're deploying with the exact values that you need for your deployment conditions, surfacing and debugging failure modes, viewing individual predictions in any degree of detail, automatically surfacing commonalities among images in your failure cases, creating and curating high-resolution test cases, searching through your image data with the natural language interface to pick out images like this one with a car parked on a city street and use that to make test cases with hundreds or thousands of examples in minutes. Automatically curating ground truths in platform such that you don't have to keep looking at noise and you can remove them without disruption. And then integrating into your existing testing pipelines with our Python client that you can use to automate your testing, deployment, and test creation here. Of course, this wouldn't be possible at all without open source. It goes without saying, but I really want to make sure that it doesn't go unsaid here, that the Python open source community is truly outstanding, and they are a foundation point of everything that we and other teams do here. And if you work on or contribute or support in any way, or even come to meetings like this, thank you very much from us from the bottoms of our heart, particularly if you've worked on the PyData Sphinx theme, which is what we use to render our documentation, which you might have noticed over here if you've got a sharp eye. There are just so many amazing tools here that really make it make us able to build kind of amazing products relatively quickly and have a amazing community to fall back on, and a very open one that we can contribute patches to as necessary, work with authors to make sure that gaps are covered really quickly, and upstream our changes to make sure that everyone's benefiting from the work that we're putting in to improve these libraries. So thank you everybody for listening. I don't know how I did with time here because we started a little bit late, but if we have any time with questions, I would love to field some right now.
Yes, thank you, Gordon, for this awesome presentation. We do have one question from Mark Broich.
Okay.
Has anyone encountered the following, in situation? How would you explain, model inference result on GPU not equal to model inference on GPU on the same system? Glad to, I had an integration test to spot it, but what is the cause? Mark, could you unmute yourself if I did not say that correctly?
Yeah.
Thanks for reading it out. Thank you. Appreciate that.
So this is definitely something that can happen, especially if you're running on a different engine or you're packaging your model. But it sounds like in this case, it was just the same engine, but either GPU or CPU. And if you see differences in performance there, I would say it's most likely to be different float handling in the GPU and in whatever float processor you have in your CPU here. There are lots of edge cases with floats, and not all silicon implements the exact same strategy. And float error tends to add up as you perform lots of these computations. And so if you have a model that is maybe 100 or more layers, and in each of those layers you've got thousands and thousands of neurons, the floats that you're multiplying together and then adding together, it is very, very possible that small changes in the implementation between these different hardwares led to substantive differences in predictions.
Thanks, Gordon, for the response. Appreciate that. What's the fix though? Distill the model onto the deployment hardware?
Yeah, the fix would definitely be to make sure that anything that you know that you can't fail on, you're testing in as close to deployment conditions as possible here. Typically I wouldn't expect to see huge differences across CPU or GPU or different GPUs. And I don't know if you saw just maybe one that flipped another direction, one that was a success and is now a failure, maybe the other way around. But the way that you would minimize that is by making sure that the testing that matters a lot is happening in that integration stage where you have the exact code that you're going to use to run it, the exact runtime, the exact hardware, and you use those numbers as the ones that are the most trustworthy, and everything else as some sort of lossy indicator maybe of what things will look like actually in deployment.
Thank you, Gordon. I mean, I'm yet to evaluate the magnitude of the problem.
That's interesting to hear about, though. Thank you for sharing that.
Yeah, thank you, Gordon. James Manis was wondering if you could drop your email address in the chat. James must have some, willingness to connect with you.
Yeah, absolutely. I'll post that there. And thank you for the reminder, James. I want to put a plug here. We are hiring for front-end, back-end ML engineering roles. And anybody, if they think that they could contribute to an early stage, seed stage product like this, we would love to talk to you more. And even if it's just an informal chat, so that we can get a better understanding of each other, I would love for you to reach out to me, and I'll send my email in the chat here.
Great.
Let me see if I can stop there.
I do have a quick question as well, a couple of them actually. So first of all, thank you, Gordon, for taking my offer up on this. This has been a really nice talk, and I hope the community liked it as well. And I would love the community to also speak up if you have seen these problems, if you can relate with these problems. I, as a team lead, I think most of my time is actually spent on getting the business to crystallize the success metrics. And most of the times that is the hardest thing to do. because nobody really knows what success is, especially early on in a research project. So that has been my pain point, and I think this framework, this thought framework as well, helps with that early on in the game. Personally, but I would love to know what the community thinks. The second part to this thing is, how do you handle drift? And like, how do you quantify drift in these test cases? Because if the data drifts too soon, then the test cases, the work of creating those test cases kind of changes. How do you propose handling that scenario? And I'll stop there.
Yeah, I can leave it up to the community right now if they want to answer that first one, or I'll hop on the second one if nobody wants to jump in. Cool. So about data drift, all I can say is that the last thing that you want to do is sort of put together perfect tests and then imagine that they're perfect and that nothing ever needs to change. As you said, data drifts, your understanding of your own domain changes, your ability to collect and successfully annotate data evolves as you mature into a project, and the tools that you might be using also change. You might be able to later on more effectively find a lot of examples that are interesting to you in ways that you couldn't do early on. And all of these things contribute towards the general recommendation that you never freeze anything. You should be constantly updating your tests to be as close to your understanding of your product objectives as possible. And that involves, in a platform, in a test case management platform, you should have the ability to version all your tests. And that test case platform should be the one that's figuring out, if I want to compare this new model that was run on these new versions of these tests against this old model that was run on these old versions, it should be able to figure out what the shared examples in those test cases are and compile your metrics against only that shared set. You really shouldn't get into a point where you're like, oh, I just don't want to change my data set because I don't want to lose the ability to meaningfully compare against past models. Or you don't want to say, okay, now's the time that I'm changing my data set. Goodbye to any sort of historical tracking. That's really just a data management platform, a data management problem, and it should be solved by a testing platform.
Also, is this work available open source, or like how is the platform being proposed to the community?
Yeah, it's an enterprise product. We're looking to launch a freemium version of it, and with that, we would also open source our client. But it is, as you can imagine, something that's changing a lot right now and relatively early. And so all of that is probably, I would say, at a minimum, a year, 18 months away. But it's on our radar. We definitely want to make sure that we can get this in the hands of people that need good testing and that don't necessarily have the ability to sign an enterprise contract.
Sounds good.
All
Yeah.
right.
So actually, I wanted to. This is Matt Phillips. Wanted to ask, maybe give an excuse to plug the product some more, because I feel like this talk was really interesting. I like starting thinking about things from a testing case first, right? Machine learning is maybe mature enough now that maybe you can start to do this. You can turn it into a big software engineering problem, essentially, or kind of take the same kind of mindset. But it's like, well, I've heard your talk. I saw that nice flow chart. But how does any particular product help? How is any product going to be actually worth it to me to even learn, even if it was free, right? As opposed to just kind of absorbing the philosophy, saying, thanks, and then thinking about how I can, come up with a more test-centric approach and sort of, focus in and talk more with business people or the business side and establish these test cases earlier. Like how does, I can do all that, just by myself, right? What does your product actually add? Which is, but take this as an excuse to just plug Kalena more.
Yeah, it's a great question, Matt. I appreciate you asking it. If the only thing that you get is this general idea of what good testing looks like, and you keep that in the back of your mind, then I think that this is a success. You certainly don't need to immediately be jumping to use our product or a similar one after this talk. But that being said, I think that the big question that we get from a lot of people is yeah, this is great. It seems like a lot of work to set up. And a platform, I think, can offer two main differentiators there. One of them being a bit what I was talking with Dhruv about earlier, the management of these test cases and the data problem of figuring out, I have this old model, I have this new model, give me an apples to apples comparison between them if they've been trained on extremely different sets of data. That is a pretty big, important piece to allow you to decouple your model training and your test evolution from your ability to generate meaningful reports and meaningful deltas as you move forward as a team. But that's just a software engineering problem, really. The second main thing that a platform offers is the tools to create these test cases. If you have a lot of images and you are very likely only annotating them for the things that you're actually training your model on, you're probably not paying teams to add annotations that are non-critical, like non-critical metadata. And that is an expensive process. And it's something that most teams are not doing. Some of them are, and some teams are doing things like training classifiers to automatically enrich their data with these metadata tags, but that's something that is very much an afterthought. And testing platform can provide you with tools to actually create those tests relatively quickly here. I think that there are a number of technologies that, particularly for images, are reaching maturity, such as like image similarity search, where you can pretty quickly and pretty effectively surface images with similar features. And you can do the same thing to build a natural language search interface where, like, I demoed it for a very brief amount of time on the presentation, where you can actually take an embedding, take a phrase, let's say like a photo of a car on the side of the street, and map that into the same embedding space as a bunch of embeddings that you've extracted from images. And you can just find embeddings that are similar to that new embedding from your text query and use that to actually search through your data in a natural language way. And this is how you get a data set that's 1 million or more images, and that's how you effectively cut through it and make these fine-grained test cases. And that tooling is not easy to develop. It's very labor-intensive, and it involves a lot of pretty tight focus, I would say, on the UX of searching through data and creating test cases from it. And I would say that that's one of the main value adds, really, that you get from a dedicated testing platform that would be very difficult to roll yourself.
Okay, thanks a lot.
All right. Great conversations. I like it. Thank you so much again, Gordon, for the awesome presentation. We kind of short on time. Let's go ahead and
I'll skip my slides. Yeah.
No worries, Gus. Still, we need to introduce Gus again. So Gus is a recurring consultant that fed to soft development.
Yeah, actually, sorry. Could I jump in on that quickly? I'm not a consultant. I previously worked at some DC area consultancies.
Oh, really?
I've been in software.
Okay.
Yeah, I've been in the software business for a while now, so similar to Gordon. I worked at a company called Anaconda, which maybe the PyData community is familiar with. And I met somebody there named Matt Rocklin, who created an open source project called Dask. And Dask is great for scaling up workloads, Python code from your local machine to a cluster and back. And I give as one of the many, one of the people that he then started a company to provide an enterprise version of Dask, which I would love. Hopefully someone can ask at the end, like, well, why would I pay for some enterprise version of Dask? What I can't do myself? But mostly what I'm here to do now is just evangelize a little bit around Dask itself. And I will show a slide or two, and then I'm going to jump into some demos, and hopefully we have a little bit of fun. And I will keep this, I'm going to try to do this in 15 minutes. So I'm going to go really fast, but if you can see my slide, can you see my screen really quickly? Let me verify, given my embarrassing foray earlier.
Yeah, yes, we can see your slides now. Yeah.
Perfect. So I think, let me just jump in. This is kind of the world that we know. I made this graph up, right? But there's lots of data. And if you have Python on your local machine, you can process it with pandas, with NumPy, with just writing Python code. Dask comes in because it will help you scale up vertically to all of the cores on your local machine. So you have a pandas data frame. It works on a single core. You want to use all of those cores, you import Dask. We're going to show you how to do that and scale up to all the cores on your machine. If your local machine has GPU cards, like you've got a Tesla V100, you can use Dask and it will scale up to all of those GPUs. It's really nice. You can also scale out to clusters, and I'll show you a fun example of that in a second. But most importantly, and this will be the main theme of my talk here, is that when you have existing Python code, you don't have to reinvent the wheel. And what I mean by that is, if someone's written scientific code to do something, and so maybe it's testing, but maybe more likely it's some sort of numerical calculation, you can Daskify it and you can run it across a big cluster. Very unscientific, but it can be very, very effective. So for those unfamiliar, and I'll jump into slideshow mode for a second. This is a quick, there's a fun little graphic of Dask, but here's the core idea. If you're used to using things like pandas, NumPy, import pandas as PD, read your CSV, it looks exactly the same in Dask. You get a high-level interface, arrays, data frames, scikit-learn style estimators for scaling things out. Sure, there can be problems along the way when you scale a bit, when you get to big scale, but this is the interface that people like, and we'll see a split, and it's a growing community of people who'll say, I'll try Dask versus something like Spark, which is your standard big data processing tool. With Dask, you can run it on your laptop, pip or conda install it. It works really nicely when you have a machine with lots of cores or GPUs. It also runs on clusters, and we'll cover I'll just jump into demos. You can see all three of these. But before I do, very, very important. If you're going to scale things up, you're going to run on a cluster, and you're going to use Dask, you should know when not to use it. There are a couple of key things you should probably do first if you're following a good software engineering practice or a good scientific practice. Use better algorithms, like maybe there's a way in NumPy or Pandas to do what you want to do without going to Dask. Maybe you can use a better file format like XAR or NetCDF or Parquet. Maybe you can compile your code with Python or Numba. If you're not aware of those tools, Numba for one is really cool, just-in-time compile tool. You can always sample, or sometimes you can sample. And then you can also profile your code and look for where the bottlenecks are before you scale it. But I posit to you all today to not do those things. Instead, we are going to take the equivalent of gripping it and ripping it. So grab your code, get a cluster, or use all the cores in your local machine. Let's just scale the heck out of this thing. Okay, so enough of this. Can you see my terminal now? Can you see my shell? This is so embarrassing if you can't.
No, we're still on the.
Okay, then we're gonna jump right into the dashboard. So here's a calculation, just generic scientific workload I'm running. I'm running this on a cluster. It's a Dask cluster. This cluster is composed of 4 machines. Each of these have 2 workers apiece, and this thing is plodding along. So what I'm going to do is I'm going to scale up the number of workers here. I'm just going to scale this up really quickly. And this cluster will respond in a second. You can see it starting to plod here. This cluster will accept the new workers as they're provisioned. These will be VMs in my case from a cloud provider. But however I've deployed Dask, it doesn't matter. This could be 10 virtual cores on my laptop, on my VM, and I have 100 available. As these additional resources are added to the cluster, Dask will just automatically start applying the computation to them. It'll take about a minute here, and we'll see this go much, much faster. So a core idea of Dask being, we can be scientific, we can be clever, we can figure out how to make things run, or we can simply scale the work that we're doing. And when these workers get added here, please go ahead and add to my cluster, please, pretty please. You'll see these come online, and this computation is gonna speed up. And I'm gonna give this one more deep breath, and then I'm gonna move on. Come on, machines, don't embarrass me. Let's see. Okay, with that, in the interest of time, we're gonna keep this thing moving. So let me show you a really quick example of Dask locally, and this is how most of you will use it. So I'm gonna create a simple NumPy style array. And when I visualize this, Dask has this nice, oh my goodness, how beautiful here. Oh, lovely. What a great start to my demo. Let me pip install this really quickly. Actually, you know what? No, I'm not going to do that. We're just going to jump in. We're going to jump to the big example. So I'm going to show you Dask on a cluster here. So when you work with Dask, you'll typically just import Dask array or Dask data frame, and you can go forth and do whatever you'd like. You have the option, and it's a very nice one, of running a local cluster. And actually, let me just show you what this looks like. So when I run, or when I choose to run, I'll open up a new notebook here. And we'll copy this cell over. Dask gives me this very nice option of running something called a local cluster. And let's just take a look at what that is and what that means. This means that I have access to, I can see what I'm running on my local machine, and soon, we'll see in a second, running on a cluster of machines. But the idea being that I can profile, and I get this wonderful dashboard for understanding what's going on. So with my local client here, I have access to 12 threads, 4 logical cores, and 16 gigs of memory. And that's nice. And now I can do stuff. I can import Dask data frame. I could run through this simple Dask array example here. and I can start to run operations like adding things together. I can transpose, whatever the standard stuff I would do. Behind the scenes, Dask is going to build a task graph for me. It's going to, in theory at least, and hopefully in reality for most users, it's going to hide the complexity of all of this. And when you do something like a dot product, Dask will be building a task graph behind the scenes to execute this code in parallel, even when it isn't really that parallel, when it's not embarrassingly parallel, when there are lots of things that need to connect to each other in a nonlinear fashion. Dask will handle that logic. That's the core of what it does. And so as you start to build more complex operations, your code is going to look like standard NumPy pandas code, and Dask will be building relatively complex graphs behind the scenes. So then when we do things like actually have some sort of standard for loop or Python style code here, go ahead and import Dask. If I go through and run this and execute this code, it will execute serially. So in my case, let me jump this over really quickly into a simple interface, make this a little bit bigger. We'll execute these functions, inc, double, add. Some of these could be run in parallel, but by default, Python's going to execute this one by one. And so when I run this with Dask, I can simply wrap my functions I can annotate this with Dask code and say, Dask, please run this function, please build a task graph for me, and it will automatically parallelize the code that I've got. This is kind of the grip it and rip it concept. So I'll pause for a quick second because I've gotten a little discombobulated. I've moved a little quickly. But what I'm going to show you next are financial services examples. So we're going to run through like a credit risk model at scale with a big 300 node cluster with a couple terabyte with a ton of RAM. And then I'll show you the similar thing on the GPU setup where we'll have a local GPU and a remote GPU cluster. But let me pause just in case I've lost too many people. Dask, scaling Python, scale up on your machine, scale out across clusters. Feeling okay for the moment? All right, great. So let us look at an example. So in this case, now I want to do some credit risk modeling, and I'm picking this kind of as a generic financial services example. We could also do some back testing. It's a very common operation. And in either case, I want a really, really big cluster. In this case, I've got lots of data. And so I'm going to go to a company called Coiled and tell them to give me a Dask cluster, but that's not my only option. I could deploy Dask myself on Kubernetes. I could spin up a bunch of VMs. I could buy a bunch of servers, plug them in, and pip install Dask on all of them, and I would end up with the exact same thing. Dask installed on a bunch of servers that I can then use. This is just a little Python client that gives me access to lots of machines, so it's probably faster and easier than that, but dealer's choice. So in this case, I end up with this big cluster, and I've got this cluster dashboard over here that's going to show me what's going on. So you can see in this case, I've got a couple hundred workers, I've got a lot of RAM, and I've got some existing computations. And then this dashboard, by the way, is just available for all clusters. That's not a Coiled specific thing. It is a Dask feature. So I can quickly rip through this data set. And if I do things, let me just make this a little bit easier to see. Hopefully that's slightly easier. I don't know. This code here, Dask data frame, read CSV. We're reading in tabular time series data. When we do this, it should look just like pandas. It's mapping the API. We can then implement our backtesting strategy using standard NumPy code. And the only difference here between normal NumPy and Dask is that when we execute this, Dask is lazily evaluated, similar to Spark. So we'll explicitly call compute, which is going to tell Dask to execute our computation on the cluster. We'll then follow the pattern. We'll calculate the return for our strategy. And when we want, and here we go for our big part of the show, we're going to go ahead and execute this from instead of 50 gigs of data for one ticker symbol. We'll go ahead and kick this off for all of the data in our sample, which is like 1.3 terabytes of data, running our backtesting strategy. And Dask is going to build this task graph, and it's going to start executing this. You're going to see this happen. It's a little choppy here because of the data volume, but Dask is going to churn through this for us. And when I need more workers, or if I want this to dynamically scale, there's a Dask setting for that. I can have adaptive scaling, or I can be very explicit and say, I want 500 more, I want GPUs, add them to the cluster, keep running. I'm eliding some of the difficulty with this, but not much. It's pretty straightforward. Import Dask, get Dask on a cluster of machines, start running stuff. And if you'll check your dashboard here to see how things are running, you can take a look at your tasks. If it's running too slowly, You can add more workers, or you can profile. If that makes sense. All right, I'll let this one continue to run, and I'm going to jump over to a GPU cluster, and hopefully my other tab is available. Could someone confirm you can see Google Cloud Platform Vertex AI here?
No luck. I think we're stuck on the original window. But if you want to try sharing your screen again, there should be an option for the full desktop instead of just the window.
Yeah, you know, I tried. It's so embarrassing. How in year 3 of the pandemic am I struggling to share with teams? That was my original, was the share full screen, and it failed. I think you can see it now. At least I shared the window.
Yep, we're on now.
Okay,
yeah.
Excellent. So for many people don't have access to GPUs, or whatever your situation is. If you're testing stuff, if you're playing around, one relatively inexpensive way to get access to a decent amount of GPU power is through the cloud. I have a strong preference when I'm paying for it to use GCP and to use their managed notebook provider, Vertex AI. So they give me access, or they'll give you access to Jupyter Lab, and you can pick a machine type that's relatively modest, that has something like a Tesla T4 GPU that's relatively inexpensive. And by relatively inexpensive, I mean, I think the list price here is like 37 cents per hour for this machine, versus the same in AWS SageMaker is like 75 cents. And it gets way more expensive if you pick powerful GPUs, if you start going with the larger instances. The T4 is fairly modest. The trade-off of that, though, for being less expensive is it's not necessarily that powerful. So there's a kind of an open source has helped us a ton here. And in particular, there are 2 projects to thank. Of course, one of them is going to be Dask, but the other is Rapids. So if you're unfamiliar, Rapids is mostly from the NVIDIA team. And what they've done with Rapids is they've taken the same Pandas NumPy style interfaces, and they've ported them over to run on GPUs, specifically to run on top of CUDA, the standard GPU driver. So this means, just like how Dask and the Dask data frame interface let us read CSV across clusters of machines, we can do the exact same thing now across GPUs, or machines that have GPUs. Read CSV, I can do Panda style operations with a package called QDF. It looks just like this. I'll go ahead and read in this kind of canonical big data set of the day, the New York City taxi data set. I'll pick 1 month of data and calculate the mean on it. And this operation I won't show you without the GPU, but would take a decent amount of time without the GPU. With the GPU, it takes just a few seconds. So it's relatively fast. Now, I picked the cheaper T4 GPU because I didn't want to spend a lot of money. And I picked a smaller instance, 4 cores, 16 gigs of RAM, because I didn't want to spend a lot of money. This also means then that I'm going to be limited in what I can do, even with QDF and with the Rapids tools, using them natively. And Dask has a native integration with Rapids. So what this means is, and I'm going to show you my little client. I'll show you my client here. Oh, come on, come on. Live demo hell here. What I can do with Dask is I can use the integration between Dask and Rapids to create a local CUDA cluster. And what this would have shown you is the fact that now I can use, if I had multiple GPUs on this machine, I can use all of those GPU cards directly with Dask. So now in this, and luckily the code has been executed so I can show you, but I can edit that line of code and say, instead of reading in just 1 month of data, I'm going to read in the entire year. I'm going to go 12 times as much data. This would take significantly longer. In fact, if I ran this on this 4-core 16 gig instance, this line of code would crash on this small instance. I could vertically scale, that'd be one option, and spend more money on compute. Or I could import Dask QDF, create my local Dask cluster, and now I can run this, and Dask will be very nice about spilling to disk, utilizing all of the cores on the local machine, using all of the GPU cores, and it will complete in a couple of minutes. So for the average Python user out there, if you're stuck on fixed hardware, even if that hardware has a GPU, Dask can be a really cost-effective way of scaling your workloads on that single machine. It will scale up very nicely, which will save you money. And then when it's time, if you all of a sudden say, well, you know what, I'm willing to spend a little bit of money. I just don't want this to run in 3 minutes. I want this to run in 30 seconds. I want to set how long this takes to run. Then you go get yourself a Dask cluster. And you can do this with services like Coiled or by installing Dask yourself and ask, give me 50 instances with GPU workers on them, and then go ahead and run this exact same computation. And now it will take 13 seconds instead of 3 minutes. And if again, I can get this down to almost as fast as I'd like it just by adding more workers to the machines, if that makes sense. So I'll pause there. We're coming up. I think I said I'd do this in 15 minutes. I'm relatively close. I've got some closing slides on deployment to show you. And I'm per like divine Dask law, I also have to show you the dashboard just a little bit more as it's starting to rip through. And we'll see if I got my 10 workers. Yeah. Here we go.
Yeah, real quick question. I think one of the clear advantages I see here on PySpark is the whole GPU processing capabilities with Rapids, right?
On PySpark?
Right. Like, so PySpark does parallelization, but this does it on the GPU as well, right?
Yeah, and I disagree that I guess I shouldn't say I'm being argumentative. I'd be very curious to learn more about how well you've worked with PySpark on the GPU. We tend to hear a lot of struggles there.
Yes, I haven't done any kind of GPU PySpark yet, but this seems like a way to do this. Right? It's a natural evolution to that.
Yeah, it is. It is, and most of the Dask use cases, like most of the Spark use cases, and maybe most of the Ray use cases are still CPU machines. But I show the GPU stuff because it's a little sexier and exciting, and it does. There is an explicit integration or a native integration with the Rapid suite of tools, which is the kind of PyData entry point for most people. Granted, again, for most GPU users. So if you segment out, like if you're someone using a GPU and you know Python, you're probably familiar with Rapids. And Dask is a nice way to scale Rapids, especially on a single machine that might have more than one GPU card. But I suspect most people are probably not using GPUs most of the time, right? Yeah, sorry, I kind of barnstormed through that question. I apologize. Let me wrap this up then with just a quick word on deployment. So I'll jump back into slideshow mode. Jacob Tomlinson is one of the NVIDIA guys where you can run Dask. Remember, you can pip install it, run it on your local machine. If your company, your organization has a cluster, HPC like Slurm or something like Singularity, go ahead and run Dask there. You can run it on Hadoop if you still got one of those old Hadoop clusters. Heck, you can even run it on Databricks, although it's unsupported. And it runs great on Kubernetes too. You could also use a managed service, so you'll be more productive, but you'll have to pay a little bit of money. Maybe something like Coiled. If you're going to install this locally, here's just a random smorgasbord of little Python quick start commands. So you'll see things like this. The core idea is that you'll always end up with a cluster object, whether that's from your Slurm or PBS cluster, whether you're using the SSH tool, whether you're using Yarn, which would be Hadoop, or let's say the Helm cluster object from Dask Kubernetes, you always end up with a cluster object. And this is really nice. So that means when you start locally, you'll always start on your local machine, almost always. You'll always prototype with a small amount of data with a sample. You'll tell Dask, give you this local cluster. From there, you'll scale using the cluster that you need. So most of the time, you'll stay local. Most of the time, you'll be able to run, you'll be able to switch between local development and then scaling to a cluster, even if it's still in a development context. Won't be much of a hassle. It's basically a one-line code change. And then on the team, when you get to the team level, when you have multiple people trying to use a cluster, the typical things we'll see, there's a service called Dask Gateway, which is open source, which is wonderful. There are tools called Dask Cloud Provider, and then there are commercial tools like Coiled. Similar idea. Hopefully Coiled is the easiest, but the idea being, hey, here's the number of workers I want. Here's how big I want them to be. Here's what software dependencies I want on them. Just give it back to me as a user and let me go on my way. So to conclude, right, there's lots of ways of doing high performance Python. In fact, actually, let me grab it. If you haven't read it, make sure you read Ian Oswald's High Performance Python book, right? He'll give you all the ways of doing this, or you can just grab yourself a cluster and go nuts. And again, my apologies for the screen sharing issues from the beginning. That's what I got. Happy to show more Dask examples or take questions.
Thanks for the presentation. This is Mark. I'd like to ask an edge case question. If the code was written in a very silly way, meaning no respect for common sense algorithms and data structures. Horrible runtime increase with increasing data volumes. Would Dask still do the magic?
So it certainly can, and that's kind of where you to a certain extent force your hand into probably paying someone like us to just make sure you had an auto scaling cluster that kept coming up. You will run into common, if you did that on a fixed size cluster, the scheduler would probably start to deadlock at some point. It would get overwhelmed. The Dask scheduler is kind of similar to like the Hadoop name node, but this is where, like, you know, full sales pitch, we wouldn't necessarily advise you on this path. But using some sort of auto scaling cluster, yeah, your code can be ugly. The cluster will say, oh gosh, I need more workers. As long as your cloud account will provision them, it'll grab them. Not a best practice, but very doable.
Okay. So you're saying if the code is complete nonsensical from a runtime point of view, a lot of improvement possible, you can still brute force through it with Dask.
Yeah, just like you could run it if it runs locally on some sort of subset. I mean, then it's going to run. Dask is Python. It's going to run on a cluster, and you'll get the benefit of all of the cores across all of those machines. So in the event that, yeah, it's really inefficient code, it's smelly, it's terrible, but you can keep adding machines. That's also maybe where you'd want some cost control and some other things in place to say, gosh, whoever that person is running that, don't let them exceed X, and at a certain point of time, start killing some of their workers, and, you know, maybe handicap them a little bit in terms of what they're allowed to do. Those types of cost control mechanisms, team control, if you will, are good things to have. Another pitch for Coiled, because we have those types of features. But generally speaking, we would say, hey, you should probably maybe take a Dask class, talk to a Dask expert, work with a consulting partner, something like that, to improve your code, you know, of course.
Okay, sounds good. Thank you.
Thank you, Mark, for the questions. Anyone else? We still got several more minutes to ask questions. If not, I mean, Gus, you really don't have to rush it, to be honest. You do have plenty of time, because our session, you know, runs through 8:30.
I thought we were till 8. I apologize.
No worries. Yeah, but really great technology and open source, you know, app, you know, packages. Everyone can try it on, and really awesome demo. Because we encourage such a, you know, a demo in our presentations, right? Because even in our lightning talks, you know, whenever you got even a really small project that you want to try out using either Jupyter Notebook or PyCharm, you can always show it in any of your presentation in this you know, platform in our event. This is all you know, encouraged and very you know, making a lot of good conversations to start with, right? So okay, I saw some comments from the chat. Matthew Mori said someone did not pray to the demo gods.
Yeah.
Oh, thanks for the presentation. Yeah, that's a good one. And Mark also thanks a lot for the Dask presentation. Really insightful, and maybe, you know, give it a try, right? And anyone has any comments? Please feel free to unmute yourself. I think Drove, you have something you want to say?
I think that I just posted a comment. I think it was a great presentation, Gus. I wish we had communicated earlier around the timelines. you probably could have used the time even further.
Correct. Yeah. Oh, by the way, Joe, do we have anyone who would like to present in the lightning talk session? If not, we can, complete earlier. I mean, it's a matter of, anyone who want to present.
Yeah, I haven't seen anything come along, but I would love to hear from anybody. If they have a lightning talk, you're more than welcome to.
Yeah. Even with a really small piece of Python debugging, that's still worth to have a, lightning talk. And remember, this is your platform to communicate, right?
Yeah.
All right. We're right on 8 o'clock, which will be the starting point of the lightning talk. But if nobody wants to present, I think we'll be fine, right, for this session.
Yes. Right.
So what's your thought, Ted? Anything you want to speak up?
Maybe I'll just pitch a question. I don't have a lightning talk or anything like that, but I could happily pitch a question to the group that might have a very short answer. It's something I haven't thought a whole lot about, but right now we're in a place where we have both a local cluster and a cloud environment that have different data on them and different technology built against them. I imagine a lot of people or a lot of companies at some point have found themselves in a similar position. Wondering if anyone here has experiences and things that worked well or horror stories of how do you blend a local and cloud-based data platform?
Great.
Can you say a little more about your current tooling and what you mean by on-prem cluster?
Yeah, so our on-prem is a Hadoop cluster running Spark.
Gotcha.
Yeah.
Is it like CDH HTTP or something you rolled your own?
It's mostly rolled our own.
Okay. So, and is it running on bare metal or are you running it on containers?
Bare metal.
Okay. Then what's the cloud look like? Sorry.
Cloud is AWS.
Gotcha. And then you also running Spark in AWS with EMR or something?
That's right.
Okay. That's interesting setup. And then I guess maybe are you currently, and not to ask you to self-diagnose your problem, but are you currently experiencing problems around data access, like data that's in HDFS versus data in S3?
Yeah, for sure. I mean, we haven't even started tackling that yet. It's more of a like, hey, we've got these two platforms, we should merge them sometime.
I see. And is there a SQL layer that you guys use? Is it mostly Spark SQL or
yeah,
do you have like a Snowflake or something?
We don't. Well, I say that. We actually do have Snowflake databases. We haven't put them in the middle.
Okay. But there's no Impala or anything. There's not a lot of Hive on-prem that users are going to try to migrate?
No.
Interesting. Okay. That should make it a little bit easier. Thanks for clarifying. I'll shut up for a second.
Yeah, I mean, I think my goal is not necessarily like solve our problem exactly. There are a lot of people working on that who are not me, but more just that I think as a data science practitioner that there's a lot of benefit to either platform, and being able to blend across them might be really nice. But I haven't heard a whole lot from the community of people who have done that and what that work environment looks like.
All right, great. Thank you, guys.
Sounds like not a whole lot of experience out there either.
Well, I mean, I do, but from the vendor perspective, I can share what people typically tell us.
Sure.
I mean, one common problem is IAM permissions with S3 data. So typically, you'll do this lift and shift from HDFS to S3, and then users will say, I used to be able, via Hive or whatever it was, I was able to get access to data. Now I can't. Are you able to get, can you from your local machine run like AWS S3LS and see the exact same things as when you run a similar command with HDFS from your terminal?
No, we're not hooked up to that yet. I guess in theory it could be, but we aren't.
Yeah, that's very common. If you don't have data, typically, obvious point, data scientists aren't too effective.
Yep.
Did someone tell you like, hey, we're going to be setting up IAM permissions and we'll give you, they probably won't want to give you like an actual token, but they'll give you a role that you'll be able to authenticate with. And
so yeah, I guess that's probably going to happen sometime in the next year. It's very things of, hey, we should maybe think about merging these, right? Like really, our work, in our situation, our work happens out of the on-prem cluster, and we have an opportunity through kind of an acquisition to move to the AWS environment, where there's more like a CDP or a standardized data platform.
Okay.
So
and leverage. It's not the. Okay. One pattern we see a lot is for people to run Spark on Kubernetes or on Glue. This is another service that does like really fast Spark clusters in AWS. But the data access is almost always the problem versus like how to get a compute environment.
Gotcha.
It's a little strange. I mean, it's a bummer they haven't given you access to it yet. Gosh, have you run anything in AWS so far? Like where you bring up local data?
Yeah. We can do that.
What services have you used?
We're in like Lambdas and S3 and what's it called? The notebook environment.
SageMaker.
SageMaker, thank you.
Yeah. Well, I mean, one hack, I showed it with GCP, but the same thing holds true for SageMaker. Also, another common pattern that sucks for users, but is that IT will say like one of the only services you're allowed to use is SageMaker. And then you're going to be they won't let you spin up your own EKS cluster or spin up your own Spark cluster using another service. So you'll be kind of stuck, and you won't even be able to go to EC2 directly. But within SageMaker, you can vertically scale the heck out of those machines. So they may give you a subset, but you can get some really big ones. And then similarly, like if you install Dask on it, you could get similar parallel behavior for any code that you run across those GPUs or across all of those. Just get like a big X1 machine with a zillion cores. Sure. It's kind of like a poor man's cluster, but you can hack your, if they're willing to pay you to leave that machine up all day, especially when you go to lunch, and just don't leave it running when you go home when you're already home. But
sure,
they'll catch you if you leave it all weekend, but otherwise, you'd probably be okay.
Cool. Yeah. Thanks for the thoughts.
Yeah, I'll shut up now for real.
No. I think this is great. Really, really glad, this is a, good bridge to communicate with each other. Really great. All right. I think we have come to an end to the March session today. Please mark your calendar on our next event date, May the 4th, 2022. And thanks again for everyone who joined in today. And I saw people already